All right, the last unit we're going to review is the electromagnetic induction, which is probably one of the most challenging ones because it puts together so many pieces of information. So we need to go through a few concepts here. First is, what is the idea of magnetic flux? And it's very, very similar to electric flux when doing the Gauss's law. It is literally how much magnetic field is traveling through a loop. Now, the one difference is it's not a closed surface. It's a closed loop. So I probably shouldn't have this integral with a closed thing, technically. It's you have a loop, and you're interested in knowing how much magnetic field lines are passing through the loop. Okay? So that's the flux. You want to know how much is passing through the actual loop we created here, and that's the idea of that flux. And you have to understand this calculation because everything we talk about in induction, in the induced EMF, depends on you understanding what that means. Now, it's a dot product. So how does the dot product work? Well, technically, if you think about an area, there's not really a vector for area, but we think about it as if you were to think a little chunk here, there is a vector that's perpendicular to the surface here. Okay, and we call that dA. So if you were to take a little area and chop it into, let's make it a side view. So this is kind of like a little bit of a side view. Okay, and you were to take a little chunk here like this. This thing has area dA. Okay, but the vector component, the dA vector, is a vector that's perpendicular to the surface, and it's also has a magnitude which is the area of that thing. So when we do this dot product, you're effectively trying to say how much of the magnetic field line is parallel to the area perpendicular. And that's what we're talking about when we're doing flux. It's like you're passing through a surface. You want to know how much is going in and going through that surface. And it's the same with electric flux. The calculation, the concept, exact same. It's just we are doing it with the magnetic field now instead. So it has to go through that surface of the loop. And that is an important calculation because the induced EMF is based off of that. So there's two things that kind of we look at. One is the magnitude of the induced EMF. So what happens is if the magnetic flux is changing through a loop, okay, you have a changing magnetic field, you are going to induce an electric field effectively. You're going to create an electric field. That electric field creates a potential difference, right? Ultimately, electric fields are related to a potential difference. So the changing flux through a loop creates a potential difference throughout that loop, okay? That's the main idea. So a changing magnetic flux in a loop. So if you calculate how much flux, doesn't matter what the flux amount is, it's the fact that it's changing. The amount of flux changing through that loop creates an induced voltage. Faraday's law tells you exactly how much that is. Now, the negative is really just to denote a bit of Lenz's law in there. Usually, I don't worry about this negative sign. I really just talk about the absolute value. But the derivative, the rate of change of the flux, is how much voltage you're going to induce. Lenz's law, it pairs together, tells you the direction of the current that will flow. You'll know a potential difference, but which way is the current flowing? Lenz's law is telling you that the current, the current will oppose the change in the flux. Okay, so that's a little tricky. So let's go through the steps that we're going to do when we're breaking down a problem like this. We're going to first find an expression for the flux through the loop. So you need to understand how that flux is. You may need to set up an integral and calculate it. You may just need to calculate. You just may need to conceptually know what the flux is if it's not a computational problem. But you need to identify what the flux is currently through the loop. You have to then identify how the flux is changing. Is the flux increasing? And the direction matters. Is it increasing into the page, increasing out of the page, decreasing to the right or left? How is the flux actually changing? Okay, and then you can figure out by Lenz's law which way would the induced magnetic field, okay, that if the current, the generated current from the voltage, right? So there's a potential difference generated, creates a current, that current creates a magnetic field. You then need to identify which way that magnetic field would go to oppose that change in flux. So if the flux is increasing, say into the page increasing, then the induced magnetic field is going to be like, I want to oppose that increasing, so I'm going to create some flux out of the page to oppose that. So the magnetic field would be opposite the existing magnetic field. I shouldn't say current because that's existing magnetic field. If the flux is decreasing, then the loop is kind of like, oh man, you're getting less flux. I want to create a magnetic field that increases the flux through there to oppose that change. So if the flux is decreasing, the induced magnetic field should be the same direction as the magnetic field. Okay, and then once we know that, now it's easier. Once you know the direction of the magnetic field, you have to think, okay, which way, by our right-hand rule with the thumb direction of the current and our fingers curling, which way the current would have to be to create that induced magnetic field. Because the current, that induced current, induced voltage, all of that we're creating because of the changing flux, will create the induced magnetic field. And once you know the direction of the induced magnetic field, you can know the direction of the current. And then if you want to know the voltage, you will take the derivative of the flux expression. So that's the main idea of how we're breaking down flux problems. Okay, the other big topic in here is analyzing RL circuits. RL circuits we analyze very similar to capacitors. Okay, so inductance is a new circuit element, right? Looks like a loop of wire, and it looks like a solenoid because it effectively is like a solenoid, or like that's a good representation of an inductor. It's measured in henries is the units of it. It stores energy as a magnetic field, 1/2 Li squared. That's very similar to a capacitor, 1/2 CV squared. So in a capacitor, it's stored as the voltage or charge. In the inductor, it's stored as current or the magnetic field. A voltage is induced whenever there's a change in the current. So for a capacitor, remember the I is equal to C dV dt. And this came from the Q equals CV part. You just take the derivative of both sides because the rate of change of the current charges the current. So it has a very parallel relationship here between capacitor and inductors, almost like they're kind of mirror opposites of one another. So here are the rules when we're doing it. In steady state, there's no voltage drop across the inductor. So for a capacitor, in steady state, we said there's no current. For an inductor, we say there's no voltage drop. That's like a short. The voltage is 0 because it's just like a wire at that point. Because this is literally a wire. It's a solenoid, so it might also have some magnetic field, which is we might have an induced EMF due to any attempt to change the magnetic field through there, right? So, but in steady state, when nothing's changing, then it's just like a wire. So there's no voltage drop. It's just a single conductor. The voltage drop is 0 volts in steady state. When the switch closes, the current through an inductor cannot change instantly, and it comes from this part here. If the current were to change instantly, then the flux would change instantly, and that would create an infinite induced EMF. And that's not physically possible. So it's got to take time for the current to change, otherwise we'd have infinite voltage. So it takes time for the current to change. So when a switch closes, so for a capacitor RC circuit, we say when the switch closes, all right, the voltage on the capacitor cannot change instantly because the charge can't change instantly. But here in an inductor, it's the current that cannot change instantly. So we focus on the current part. We may use KVL and KCL to set up a differential equation that involves a current through an inductor. So when we analyze RL circuits, very similar process to our RC circuits. You want to establish the initial state of the circuit. When they've been a long time, there's no voltage across the inductor, and you want to solve for the current initially through the inductor. Once the switch changes, the current cannot change instantly. So we're still at I0 right at that moment. And a voltage drop can appear across the inductor because now the current can be changing and there can be an induced EMF at that point. When you're waiting a long time, there's no longer a voltage drop across the inductor, right? So the voltage is 0 here, and then you can then solve for the current through the inductor. The current through the inductor will be a curve that starts at I0 and goes to the final current, and it will be exponential. And that time constant is going to be L over R. So very similar to RC. RC, the time constant was RC. Here, it's L over R for the time constant. You use V equals L di dt to find the voltage across the inductor if you need to, and you use KVL and KCL to set up a differential equation for the current through the inductor. Okay? That's the main idea. Last part, LC circuits. Circuits contain just L and C. They will oscillate. If you set up the differential equation, and we'll go through an example where you do that, you end up getting something like this. And if you remember from oscillations in Unit 7 in your mechanics, it's the second derivative. When we had these scenarios, it'd be negative omega squared times x. okay, you have another similar differential equation. You have a second derivative of charge, and you have a Q here. And so then this part becomes omega squared if you pattern match. So the solution is going to be a sinusoid, and the omega is going to be 1 over root LC. I would go back and look at some of that stuff we did on harmonic motion or oscillations in unit 7 if you don't remember setting up that differential equation. But in general, with the LC circuit, you're going to have this sinusoidal response for voltage and current, and it's really just going to be an exchange between the charge, energy stored in the capacitor and energy stored in the inductor. There's a conservation of energy and an exchange between the capacitor and the inductor when we do that, and we'll go through a problem later on. So let's go through a few multiple choice and free response questions. So we have a rectangular loop of wire that lies inside the XY plane with a uniform magnetic field in the negative Z direction as shown. So positive Z is coming out, negative Z being X's into the page here. Which of the following will an EMF be induced in the loop? And that is when the flux is changing. This is Faraday's law, or flux changing through the loop. So we want to look at this. We have flux, right? There is flux through the loop. Anything that would change that flux is going to induce an EMF. When the loop is moving without rotating in the positive Y direction. So if it moves upwards here. Okay, now the same amount, because it's a uniform magnetic field, as I move upward, it's still the same flux, right? Because the same magnetic field, because even though you have X's just here and here, it's just assumed everywhere as the same amount. So as you go up, you're not getting any more magnetic field through the area, so that's not going to change the flux. When the loop is moving without rotating in the positive Z direction, again, this is a uniform magnetic field going straight up and down, so if I go in this direction, again, I'm not changing the amount of flux going through there. When the loop is rotating along the Z-axis, so here it's like spinning this way, this is the Z-axis, so I'm rotating it again, uniform field, not going to be changing the flux. When you're rotating along the Y-axis, now we got something, because the magnetic field's coming towards you, or going towards you like this, but then we're rotating the loop. So what we're doing is we're changing the angle. So if I rotate it this way, then less is going to pierce through there. So we're going to go through the loop, pass through the loop. Eventually, if I turn it completely sideways, then the magnetic field lines will just pass by it on the sides. So D is the one where we'll induce an EMF. Okay, let's take a look at LR circuit here. So we have an inductor with inductance L is placed in series with a resistor of resistance R, battery of EMF epsilon, and a switch that is initially open as shown in circuit 1. The switch is closed at time t equals 0, and the circuit reaches half of its steady state current at t1. So this is going to be related to a time constant. Reaching half is a fraction of the RC time constant. Circuit 2 is constructed by adding a resistor of resistance R in parallel, and then it's closed, and it reaches at t2. What compares t1 and t2? Well, they're going to be both proportional to the time constant, which is L over R. Now, what are we doing when we're doing this parallel? Is it's going to shrink the overall resistance, right? It's going to come down to 1/2 R, because if you collapse those into a single resistor, it'd be half an R, and then you'd have an inductor with half an R versus an inductor in R. So T2, which is going to be proportional L over R, is going to be less than T1, because it has a, smaller resistance going to increase the time constant, right? So the smaller this goes, that's going to increase the time constant. So therefore, T2 has to be greater than T1 because it has a smaller resistance. Smaller resistance means larger time constant. Larger time constant means it will take longer to reach half of that. That's the shape of the exponential curve. So T2 is going to be greater than T1 because the equivalent resistance is greater than circuit 2 than in circuit 1, or is it because the equivalent resistance is less than? Two resistors in parallel will have less resistance, not greater resistance. So it's going to be D here. All right. So a metal of wire resistance 10 ohm is bent in a circular loop of radius 0.1 meters and placed in a uniform magnetic field as shown. The Z component of the magnetic field is shown as a function of time. The Z component is all we care about because that's the one that's actually passing through the loop for the flux calculation, where positive indicates that the magnetic field is directed out of the plane of the figure, which if following correctly indicates the magnitude and direction of the current induced. Okay, so first we want the current. We want to know the current induced, the magnitude of it, and we also want to know the direction of it. Okay, so let's go through the problem-solving steps. We first have to identify the flux. The flux is coming out of the page, right? So the flux, in this case, again, you look as the integral B dot dA, but however, actually, I keep writing that circle because I'm so used to Gauss's law, but it's technically that. Integral B dot dA, and we're doing that area there, but the magnetic field's constant, and it's just B times the area in this case. B times the area, because it's already perpendicular, or the Z component times the area if you want, right? Okay, cool. So that's the flux. Now what we want to talk about is how is the flux changing? We want to identify how's the flux. So if we're doing at 6 seconds, we're at this point right here. How is the flux changing? Well, right now we have zero flux because the magnetic field is 0 at this point. So at t equals 6 seconds, the flux is 0. That doesn't mean that it's 0. It just means that the flux is 0, or it doesn't mean the induced EMF is 0. It just means the flux is 0, but it's changing. The change of the flux is that it's going to be creating magnetic field into the page, right? Because it's negative magnetic field, so we have flux into the page, and it's increasing into the page. So the flux is increasing into the page. Okay? Now, how does the induced magnetic field here? So because I'm having more flux going into the page, the loop wants to oppose that. It's increasing into the page. It wants to create a magnetic field out of the page. Out of the page's dots. We have to induce magnetic field out of the page, okay? Because right now the flux is into the page, increasing into the page, so we want to oppose that. We're going to create some flux out of the page to compensate for that. And then we use our right-hand rule. Which way would the current have to go for the current to be coming out of the page? Well, at the top of the loop, if I want my fingers to curl towards me, right, out of the page, then my thumb has to be pointing left. So over here, it's got to be left, and then you can do the rest for the other sides, but you'll find that it then has to move in the counterclockwise direction. Okay, so it is not clockwise, it's counterclockwise. Now, how do we figure out the current? This is where we're going to take the derivative of our expression, right? So the voltage is the derivative, and again, remember, I don't put the negative sign because that's just telling you direction, and we've already handled direction based off Lenz's law, so I don't really like that negative sign. So we're going to take the derivative of BZA dt. The area is not changing, nor is the area relative to the magnetic field changing, so this is just A times the derivative of Z, and that is just the slope of this line, right? This is a slope of this graph, right? So what's this slope? It looks like it's goes over 3 and then down 0.4. So the slope is negative 0.4 over 3. And what is the area? The area, radius is 0.1. So this is pi times 0.1 squared times negative 0.4 over 3. Again, you don't need to worry about the negative sign. All we really care about is the change. So this is going to be pi. So that's going to be our voltage, right? And then, okay, we want to find the current, but this is equal to I times R because the loop has some resistance here. So to find the entire current, we're just going to divide all of this by the resistance by 10. Right? So then that's going to be our calculation. So it's going to be pi times 0.1 squared times negative 0.4 divided by 3. All of that divided by 10. And I get negative 0.000419 amps. Don't worry about the negative sign. We've already handled the direction by our Lenz's law. And so if you multiply by 1,000, that's 4.19 milliamps. And so that's going to be D here. Okay. All right. Yeah. All right. Now let's look at some free response questions. So we have a rectangular loop sits next to a long wire which carries a current I at T through it. If I at T is a constant value equal to I0, derive an expression for the magnetic flux through the loop. Express your answers into here. So we want to do B dot dA. And we got to think about the magnetic field. Now we got to go back to the previous unit. We have a long wire. It's creating a magnetic field. What is that magnetic field? It's mu naught I. You can use Ampere's law or you can just remember it. This is one that's easiest to remember probably. So here we're going to have magnetic field. Now our fingers to the right, it's kind of curling out. We know that the magnetic field is going to be coming out of the page here if we use our right hand rule. So we have magnetic field. Now, the thing is, the magnetic field is not constant. You can't just do B times the area because it depends on the radius. It depends on how far away we are from here. So to do this integral, we actually have to slice things up. How are we going to slice things up? Well, because the magnetic field depends on the radius, I want to make horizontal rectangles. very thin horizontal rectangles here with a thickness of dr, right? That's located a distance r away. Now, why don't I do like vertical rectangles? Why do horizontal rectangles? Well, I want the magnetic field to be constant in that region that I've kind of cut up. And because it's dependent on r and because it's very thin in the vertical direction, right? The magnetic field is not going to vary very much in this region right here. It's going to be about the same in this little rectangular piece that I have, right? If I make a vertical rectangle, for example, right? The magnetic field varies along this path. So it's not going to be, I can't just multiply the magnetic field times there because again, it will vary. But here, if I make a horizontal rectangle, the magnetic field is pretty constant over that region, right? So that's the magnetic field, mu naught I over 2 pi r times the area. And now it's already perpendicular, so there's no like cosine or sine angles. The flux is passing straight through it at a right angle, perpendicular to the surface. So the dot product, you just multiply by the area. The area of this thing is the length of that rectangle times how thick it is, dr, like that. Okay, and so that is the contribution of the flux there, and then we just want to add them all up. We want to add them all up from r equals, because we're integrating over r, from r equals d to d plus w. D to d plus w here. Okay, so that's going to be our setup. Now, we're going to pull out everything that's a constant. The L is a constant, the 2 pi is a constant, the mu naught, the I. And then we're just going to integrate from d to d plus w of 1 over r dr. Integral of 1 over r is natural log. Ln absolute value of r from d to d plus w. And that's going to be mu naught IL over 2 pi ln of d plus w. These are all positive values. Minus ln of d. I should put brackets here. And then last, you could leave it like this. If you want to simplify, or just for the purposes, in case you need to match a multiple choice answer, when you subtract natural logs, you can divide the insides like there. Let me just make it a little cleaner. Capital W over D. And that is going to be our answer for that. And this is I zeros instead. So I always like to check the variables, just make sure I'm using only the variables that I'm allowed to use here. And we're good here. Okay. Put I zeros just to make that. Okay, suppose the loop is pushed upward so it moves at constant velocity. Derive an expression for the induced EMF in the loop. So we're going to push it upward, constant velocity, so we don't really have to worry about the what's causing it necessarily. But we do need to know how the flux is going to change. Now, here's the thing about the flux. The flux is going to change because as we get further away, obviously it's going to be less magnetic field going through here. So how are we going to figure out what is the induced EMF? Well, it is the rate of change of the flux, dt. Now, we need to take our expression here as we found the total flux as a function of d, but now let's call this, instead of d, let's just call this x, right? Or we'll call it y, I guess. We'll call that distance y. So I'm going to replace d with y, and that's going to be, the y variable is going to be changing because, let's see, y plus w over y. And so that is our flux equation. And then I want to take the derivative of the flux with respect to t to figure out the induced EMF. Now, what's changing? This is the thing you got to think about, is what is actually changing in here? Is I0 changing? No, the current is still having the same current going through it. Is L changing? No, the length of the loop is changing. Is W changing? No, this width is changing. However, the Y variable is changing, so that's my only variable here. Okay, now I'm actually, because the derivative's easier with natural log if I just sort of like, I'm going to actually use this form, because otherwise I'd have to do like quotient rule and stuff, so it'd be ln of y plus w minus ln of y. So now you have to think about the d is changing, the y is changing. So derivative of this is mu naught I naught L over 2 pi. Then the derivative ln of this is 1 over y plus w times dy dt by chain rule minus 1 over y times, again, dy dt by chain rule. Okay, so dy dt is the rate at which the y is changing, which is, from kinematics, that's our velocity, right? Because we're moving at a constant speed, that is the rate of change that the y variable is changing, right? So we replace that with v, so this will be mu naught I0L over 2 pi times 1 over y plus w. You can factor out the dy dt. We'll just put v here. 1 over y plus w minus 1 over y. And that would be the induced EMF. Now, this will technically be negative, so you could put negative to make it positive. It doesn't really matter. The induced EMF, the magnitude is just telling you a little bit of direction, but we don't usually worry about that. It's just the magnitude of the voltage. And then that's it. Okay, so that's kind of the process for doing flux calculations. Now the loop is placed back in the original spot, but the current now varies by the equation A cosine. Derive an expression for the induced EMF. So now we go back to our equation, our flux again, back to our equation here. It's mu naught IL over 2 pi I over 2 pi. Now the current is not I naught, it's changing, right? So it's ln of d plus w over d. And now you got to think about which one of these variables are changing when I take the derivative. And honestly, it's just the I part, right? Like mu naught L 2 pi d and w are not going to change here. So it's going to be mu naught L over 2 pi ln d plus w over d. And then you got to make sure you have a di dt term here. And so what is the derivative of I? Di dt. It's just a derivative cosine is negative sine omega t, and then by chain rule times omega. So then we're going to get mu naught L over 2 pi ln of d plus w over dt times, and just make it a omega sine of omega t. You can put, I mean, if you want to be purely notational, you can put a negative sign here, and so that will cancel out the negative sign there. But again, when you're asking for the magnitude of the induced EMF, that's all that usually matters, not if it's positive or negative. Again, we use Lenz's law to dictate which way the direction of the current is going to go. So we don't really care what the sign of the voltage is. You might argue, well, it was negative voltage, but negative voltage just means the current's going to go the other direction. So use Lenz's law to determine the direction of the current. Just use the magnitude to determine what the voltage magnitude is, and then let the Lenz's law dictate the direction of the induced current, which will be effectively the direction of the induced voltage, right? Okay, let's look at another problem here. So I have a single loop of wire with resistance R and area A. So we have a loop of wire is placed inside a solenoid with the normal to the loop parallel to the axis of the solenoid here. Solenoid has N turns and a length of L and is connected to a power supply that is not shown. At time t equals 0, the power supply is turned on and the current I through the solenoid as a function t is given by the equation this. The direction of the current in the solenoid is clockwise as shown in the N view. At time t greater than 0 is the induced current in the loop as seen from the N view shown clockwise, counterclockwise, or 0. So we need to think about which way is the flux. So we're thinking about it. The current's going this way. It's looking clockwise here. Let's do our right hand rule. We need to first identify which way is the flux, and then we need to think about how the flux is changing. So right now, this current right here on the outside is creating a magnetic field, and you can either use Biot-Savart or just the right hand rule, but my thumb is down. It's going to go clockwise like this, and in all cases around that loop, my fingers point into the page, so we know that the flux is into the page here. That's the direction of the magnetic field from the external wire. And what's happening is beta is beta is greater than 0. This is supposed to be a positive value. Just accept that. I wrote that in there. Okay, so if beta is increasing, so beta is positive, so the current's increasing, we're increasing the flux into the loop at this point. So at this point, if you look at this picture over here, it's going this way. We're increasing the magnetic field to the right, so we're going to induce a magnetic field to the left. So we want to induce a magnetic field to oppose that change in flux, right? Okay, so if we oppose that change in flux, then from the N view, to create this magnetic field, the current has to go this direction. So it's going to be counterclockwise because it opposes the increasing flux through the loop. Okay? You write it out. This is not a sufficient explanation. Write out your way to describe it, but basically you just want to outline and say, like, because the magnetic field is into the loop from the N view and it's increasing, then the induced flux can be out of the loop, which means it has to be a counterclockwise current. Just write that. That would be sufficient. Derive an expression for the current in the loop of wire. Express it in terms of R. let's see, R is the resistance, A is the, R is very tricky because R is resistance. I just want to make sure it's not radius. A is the area, N is the number of loops, beta. Okay, so we need to figure out what the flux equation is going to be. Now, remember in a solenoid, the magnetic field is pretty much the same everywhere. And the magnetic field in the solenoid is going to be, the magnetic field of solenoid, and this is on your formula sheet, is going to be mu naught N times I, where N is the number of turns per length. They didn't give you the density. It's N over L in this case because they gave you the total number of turns in length L. Okay, so that's the formula for the magnetic field. So when we do this integral B dot dA, it's the mu naught N L I just times the area, because the magnetic field is assumed to be pretty uniform in the solenoid. If you're not sure about that, go back to the previous lesson where we derived the magnetic field of a solenoid in the FRQ, and you'll notice that at the ampere and loop, if you just change the ampere and loop vertically here, like where it passes through, you'll find it doesn't really depend on where it's at. Okay, that's why the solenoid equation doesn't depend on the distance there. It's anywhere in the interior of the solenoid is about equal to that. Okay, so that's the flux. And so if we want the voltage, we're just going to take the derivative of the flux. Which one of these is changing? Mu naught's not changing, number of turns is changing, length of the solenoid's not changing, area of the loop's not changing, I is changing. And the derivative of I is just beta, right? Because it's beta times t. So di dt is just beta, right? So that's the voltage. And then finally, the current is the voltage divided by the total resistance, right? So just divide that by R. So it's mu naught N over L A beta all over R. Okay, that would be fun. All right, let's take a look at another FRQ. So we have two parallel, and I've modified some past FRQs to make these work because I kind of want you to do more symbolic problems because I think that will be the, more challenging part, things without numbers. So we have two parallel conducting rails that are separated by distance d. Okay, so this is the d. A resistor of resistance R connects to the rails. A conducting bar is placed on a slope section of the rails at a height h above the horizontal section of the rails. Frictional forces and the resistance of the bar and the rails are negligible. At time t equals 0, the bar is released from rest. Position x0 slides down the slope section of the rails. As shown in the perspective view, at time t equals 1, it reaches x1. Smoothly transitions to the horizontal section, enters a uniform magnetic field B1 that is directed in the positive y direction. So it's pointing up here. Positive y. Okay, time t, it reaches position x2, so it exits this region, and then at part 3, it enters the magnetic field of B2. That is in the negative z direction. At t4, it reaches position x4 and enters a region with no magnetic field. So it's just passing through each of these points at different times. The bar is position xb at time tb, such that tb is between, so it's here, somewhere between when it's in this region. Indicate the direction of the current flowing through the bar. Okay, so why is there current flowing through a bar? Is you're having a loop, right? So you got to look at this. There's a loop right here. That's because it's a conducting bar. It makes a loop here, right? And so we got to think about whether the flux is changing. Well, there's flux from here, and as the bar moves to the right, it definitely is going to have a change in the flux, because once it moves over, you're now going to enclose more magnetic field, right? So you got to think about the flux. The flux is coming in the positive y direction or out of the page in this picture. And we're increasing flux in that direction, right? So we're increasing flux out of the page. So therefore, which way do we need to induce a magnetic field? We want to oppose that, right? So we're getting more flux out of the page. We need to send some flux into the page to counteract that. And so that will be the induced magnetic field. Okay, and if I want to induce a magnetic field and I want to go into the page there, and let's take a look at the top of the loop. I wanted to go into the page, so my finger has to curl like this, and my thumb's got to point to the left. So on the top part, my current would have to point to the left. And on the left side, again, I want my fingers to go into the page, my thumb, okay, my thumb would have to be pointing down then, right? So it's going to be clockwise here. So it's going to clockwise current, if so it's to be clockwise, or it's going to be down. So it's from the bar. So it's going to be a clockwise current going through there. And that's how we do those steps for Lenz's law. Derive an expression for the velocity bar as a function time while the bar is in the magnetic region. Express your answers in terms of this. Now, a lot of times they say it's a constant velocity of doing a force. But here, what happens when we have a current through here? So we're going to have a current through here. And that current is going to go through that magnetic field. And we are going to ultimately have a force on it, right? Because whenever you have charges moving through a magnetic field, it's going to experience a force. And so what's going to happen, all right, is you got to think about that current. It's going to experience a force. Now, if we think about the force from the magnetic field, right, it's IL cross B. So the current is going down, right? So we use our right-hand rule. So the current's going down. Magnetic field is out of the page. So my thumb is pointing to the left from my perspective, left. Okay, so we're going to have a force here. So if we look at our forces, that's the only force acting on it because it's an aerial view. There's a normal, like if you draw the bar here, technically there's gravity and normal force, right? But like, and then there's a leftward force. But in the x direction, we only have a force here. So that force is equal to F net equals ma in the x direction. So we have this net force, which is going to be ILB. Okay, and it's going to be negative because it's pointing left, is equal to m times the acceleration, which is dv dt. Now we need to figure out what this ILB stuff is. The I has to come from the induced current. It's not any current that's running the loop, it's the induced current through the loop. The B is constant, so this is B1. L is the length of this loop, so that's going to be D. So let me just make it, we're going to make it minus IL, or not LD, because that's the length of the wire in there, times B1. Is equal to the mass of the bar. Oh, I think I didn't give you the mass of the bar. Okay, mass of the bar, we'll just say is M. You are going to need it. I think you're going to need to know that. Probably going to need to know that. We'll see if we need to know that. Do the math. Okay, so now we got to figure out the current induced here. That we have to find an expression for the flux. Now the flux, the integral B dot dA, well, the magnetic field's constant. The area is going to be B times the area enclosed here. And let's just call this, should we call this variable x? We'll just call that x. And then we'll call this height d. So we just have a placeholder variable for this x. The most important thing to remember is that x is going to change. So the rate of change, the voltage, is going to be the rate of change of this. Well, the B1 and the d are not changing, but the x is changing. And that is the velocity. The rate at which this x position changes is the velocity. So it's B1 dV. So that's the voltage. So the current being V over the resistance is going to be B1 D times V over R. And we're going to plug, it's not, be careful, I'm going to put the V in front. It's not dV, just happens to be D and the letter V. So BVD. And then we're going to plug that into here. So then you're going to get negative B1 velocity D over R times B1 is equal to M times dV dt, and this is going to be ultimately a differential equation with V. So you can move the dt up and move the V down, so you get negative B D, so it's going to be B1 squared, D squared, sorry, not D squared, just D, this is a dt, over R dt. Do I have everyone B1 squared, and then dr, yeah, and then we're going to move the v to the other side. Oh, we need to move the m to the other side, so divide the m, so it's going to be dv over v then. Okay, so just confirm, pause if you need to, just confirm I did that math right, but I think I did that. V's down, dt's up, b1 squared, d, dt, r, yeah, okay. And then we'll integrate both sides. These are all constants, so it's negative b1 squared d over mrt plus c is equal to natural log absolute value of E. We've done a lot of these differential equations a lot. Hopefully you could just put E as the base, and you'll get V is going to be C e to the negative B1 squared D over MR. Okay, now we need to know the initial velocity though. That's the only thing that we can, because the C, we need to know a condition, and that's where we're going to use how fast is this rail moving at this bottom, and that's where we got to use conservation of energy. Got to go back to unit 3. And this is why the mechanic's so important, because you're expected to know these things. So our system is going to be, the Earth plus the bar, and we use conservation of energy. Hopefully at this point, you're really good at that. So the initial energy, we don't have any kinetic energy because you start with velocity 0, so you have mgh. And at the bottom, you'll have just kinetic energy. So that's going to equal mgh. M's cancel, you get the V is square root of 2gh. So when it enters this region, that's the initial velocity. And that's going to be the C here. When time is 0, oops, I forgot the T. When time is 0, this will be 1, so we need this to be V0. So our velocity is going to be V0 e to the negative B1 squared D over MR times T. Okay, so that will be our setup for that. I know it was a lot. That was intentional to make it a lot of work, but I want you to see the math part is just a portion. The setup is a much trickier part, right? That you can set everything up, and then we're just using the calculus to then solve these things. Now, after the bar exits a region B1, it moves at constant speed until it enters a magnetic field of B2. Derive an expression for the induced EMF as it travels through this region. Express your answer. This one's kind of a trick question. So it enters, so it's going to leave. Let's assume it has enough speed. It makes it through, and it goes into here. But let's think about it. If you have the bar here, this B2 is passing straight over it. There's no flux from this guy. So is the flux in this loop changing or not? In this loop, we still have the flux here. Not the flux is 0. It says the flux is not changing anymore because B2, even if we have more B2, that isn't passing through the loop, right? So the flux contribution there is 0. So the velocity bar is a function while it's in the magnetic region B1. We just need to find the velocity. It'll move at constant velocity. And sorry, I meant to say that you can use the time variables maybe on this one. Let me double check real quick. I think the main thing I actually wanted to just to make sure that you derive an expression for the acceleration of the bar. I think I meant to do this. The velocity is doable. You would have to do it in terms of how far it traveled. So you could do this and integrate to find the displacement to then figure out like how fast he would be moving at this time here. But that was not my intention on this question. I really wanted you to just recognize that the acceleration was 0 in this problem. Was that effectively because the flux isn't changing anymore. So you have to be careful. Just because they give you a magnetic field doesn't mean there's any flux. You have to be intentional. Think about what the flux is and is it changing, okay? And that's the huge part of what you're trying to do in here. Okay, after bar it moves. So that's what this part was too. Was the induced EMF. This one is just asking about the induced EMF, but the induced EMF will then be 0, ultimately, the induced voltage, and that's because again there's no change in flux in that region. Okay. All right, switchable circuit. Let's talk about an LC circuit. Let's look at the last thing we should look at here. Switchable circuit contains resistor R, capacitor C, an ideal inductor L, and a battery of EMF epsilon, as shown in this figure. Initially, switch S is connected. This is switch S here. Is connected to position A. This is A and this is B. This is the switch here, forming an RL circuit with the battery. After a long time, the switch is moved to position B, which disconnects the battery and the resistor and reconnects only the inductor and capacitor. While the switch is in position A, set up a differential equation to solve for the current I through the inductor. So we're going to do our circuit analysis. All right, so we have our plus. Well, so first let's think about what direction the current's going to go. It's going to go like this, going to go like this. So this is going to be plus, this is going to be minus, or plus, minus. And for an inductor, also make plus and minus. Our signs should still, current goes from positive to negative, okay? So we still do that. Now we want to think about, let's call this I, because we're trying to figure out what I is, and they're in series of the same I. So the voltage across here is going to be I times R, and the voltage across here is L di dt. Okay, and this is epsilon. So what is our equation going to look like? We make our loop rule. It's going to be epsilon. We go up epsilon. We're going to drop an IR, and then we're going to drop an L di dt. And that's going to sum to 0. So this is a differential equation that has just I in it. Okay? The L is a constant, R is a constant, epsilon is constant. Those are known constants that they give you. Now we want to solve the differential. We want to determine the current as a function of time, assuming that the initial current is 0. Okay? So that's going to be our initial condition. That's going to help us figure out the constant. So we want to solve this differential equation. So we're going to move the L di dt over here. Is equal epsilon minus IR, right? We want to divide this. Well, let's factor out an I, because I just want to move the I over. So we're going to factor out an I. Well, actually, I can't factor out an I. I can factor out an R to isolate the I. R is going to be epsilon over R minus I is equal to L di dt Then we can move this guy over with just the I, move the dt up. So it's going to be R over L. Move the L over, move the dt up, is going to be di over epsilon over R minus I, like that. And then now we're going to integrate both sides. Okay, so this is R over L, T plus C. And then this is going to be negative natural log absolute value of epsilon over R minus I. Okay, why is a negative sign? Because by chain rule, when we take the derivative, we have to multiply by -1 there. Okay, so we'll put a negative sign, make that positive, and then put E as the base. Right, so we get epsilon over R minus I. And we've done this a lot of times, hopefully in your calculus class. You strip away the absolute value because you put this constant in front. Is CE to the negative R over LT. Okay. And then we can now solve for the current. So we solve for I. Move the I over, move this over. You get epsilon over R plus CE to the negative R over LT. And then we just got to figure out what this constant is. When T is equal to 0, we know the current has to be 0. So when this T is equal to 0, this is just 1. So we get 0 is equal to epsilon over R plus C. So C is equal to negative epsilon over R. And so then ultimately you get I. Let's put it over here. It's epsilon over R minus epsilon over R e to the negative R over LT. And that's this part here is where we get our time constant, right? Because this becomes T over tau, which is T over L over R, right? So that's where that time constant comes in. But that's going to be our equation here. What is the current I0 through the inductor after the switch has been position A for a long time? So when you wait a long time, what's our assumption? Is that the voltage here is 0. Another way to think about it is all the derivatives are 0, basically. You wait a long time, this derivative is 0. So then this voltage is 0 here. And so then this voltage has to be epsilon right here. Because if you look at your loop rule then, when you wait a long time, there's no voltage here. So then this has to absorb the full voltage drop here. Because the drop here has to equal this epsilon. So then we have epsilon over the resistor. And then you know the current through the resistor. The current through the resistor would be just epsilon over R. Okay, now the switch is moved to position B. Assume the capacitor is initially uncharged. Okay, determine the maximum charge stored in the capacitor. So now, when we go to B here, we have an exchange of energy between the LC inductor. So the total energy at any time remains constant. It's equal to 1/2 Li squared plus 1/2 CV squared. But there's no charge because the Q is 0 initially. So right at the switch, it says the switch closes. So at T is equal to 0 or whatever. This is then, shouldn't have been 0, I guess. This should have been at like TB or something like that. So when that's 0, then all of the energy is just in the inductor, right? So it's L, and how much current is epsilon over R. So at this moment in time, this is how much energy is stored total in our system. Now, eventually, all of that energy will go into the capacitor. So for the max capacitor energy, which is 1/2 CV squared, or in terms of charge, because Q is equal to CV, it's 1/2 Q squared. So I think you do V is equal to Q over C, 1/2 Q squared over C, right? That's going to equal the same amount of energy that we had in the inductor because we're exchanging those energies there, right? So the 1/2s cancel. The C cancels. The Q squared is going to be LC epsilon squared over R. And so Q is going to be the square root of LC, and the square root of that is just epsilon over R, like that. So that's going to be the maximum charge. Now, it's going to continue to exchange between energy stored in the inductor and energy stored in the capacitor. Now we want expressions for the energy stored in the inductor and the capacitor as functions of time. So remember, what's going to happen on the inductor is the current through the inductor is going to be a sinusoid. It's going to be A cosine or sine, cosine of omega t, right? Where omega is going to be square root of 1 over LC. That's what we said about it's going to oscillate like that. That's going to be the solution to the differential equation. Now, let's think about what the inductor is going to do as a function of time because you want to figure out what that is. Why do I want to do that? Because the energy is just going to be 1/2 Li squared. And you're going to have 1/2 CV squared as well. So if I know the current and the voltage, then I can find expressions for the energy. So remember, the current for the inductor is going to start at maximum, and then he's going to shrink down, and he's going to go like this, right? So he's going to be a cosine exactly. Now, what's going to happen is once the current is 0, there's no energy. We're going to have the maximum voltage on the capacitor. So the capacitor is going to do something like this. It's going to have a 0 on the capacitor when where the current's the other direction. So it's going to be something like this. And that's because, and so this is going to be more like a sine. So the voltage as a function of time is going to be a sine of omega t. Now we got to figure out what the maximum, what the amplitudes of these are. Because we started on the maximum, right? The current he's going to start off with is going to be epsilon over r. That's the maximum current right when we started is epsilon over r. Okay, cosine of square root of 1 over LC times t. And now the voltage as a function of time is going to be what the maximum voltage is. And we kind of can figure it out here. We didn't solve for the Vmax, we solved for Qmax. But Vmax is just going to be Q is equal to CV, so the Vmax is Q over C. So it's going to be square root of LC epsilon over R over C times sine of square root of 1 over LC times T. Okay, so then that's our sinusoidal expressions for the current and voltage. And then the energy in the inductor is going to be 1/2 L times this thing squared. So just epsilon over R cosine square root of 1 over LC T squared. And the energy in the capacitor is going to be 1/2 C and then this thing squared times square root of LC epsilon over R over C sine of square root of 1 over LC times T squared. And if you wanted to, you could plot them, but you would see them, the energies would go, if you plot them, you'll find the energies will dip down, go up and down, up and down, and up and down. And you'll see the exchange between here and here, between the capacitor energy and the inductor energy. Okay? And that's the derivation of that.